Hi there. This video will cover the relationships between temperature, pressure, and volume. Um, these are the three main variables that affect gases. There are more, and we'll talk about that in the next video and at the end of this video. Um, but the three main ones that we'll focus on for now are temperature, pressure, and volume, and relationships between those variables. Now, if we're looking at the relationship between two of those variables, the third one will always be constant. So if we see in this first example, temperature-volume relationship, we see that pressure is held constant. Now, temperature-volume relationship is a direct relationship. If temperature goes up, volume goes up. Temperature goes down, volume goes down. You may have seen this if you've ever put a marshmallow in the microwave. Well, what happens is a marshmallow is made up of sugar mostly, and it's got a whole bunch of little bubbles in it. And if we heat up that marshmallow, what happens is those bubbles expand and they get bigger. So if we increase temperature, the volume increases and it makes the marshmallow expand and get bigger. The opposite is also true. If temperature goes down, volume goes down. This is called Charles' law. You don't need to know them by name, but know that they have names. Some books or people might refer to them by name. So next relationship is temperature-pressure relationship. Again, the third variable, being volume this time, is held constant. If temperature goes up, pressure goes up. If temperature goes down, pressure goes down. And you may have seen, you may see like spray cans sometimes, or oftentimes like shaving cream or hairspray or that type of thing, something that's in a spray can. It'll usually say on there, do not throw in fire, or do not incinerate, do not burn, keep away from flame, something like that. The reason is these are metal cans and they don't expand or contract. They don't stretch. The volume doesn't change very easily in a metal can. So if we increase the temperature, the volume can't change, but the pressure does. So if you were to throw one of those cans in the fire, what would happen is the pressure would build up and build up and build up, and it would finally explode. And if what's in the can is something like hairspray, something flammable, you can cause an explosion. Again, the opposite is true. Temperature goes down, pressure goes down. This is called Gay-Lussac's law, and again, a direct relationship. You'll want to be able to recognize these graphs. Next relationship we're going to talk about is between pressure and volume, and in this case, temperature held constant. If we think of, we got a bag of chips, one way to open a bag of chips, it doesn't work very well because it crushes the chips oftentimes, is to squeeze the bag. You squeeze a bag of chips, and the pressure goes up and the volume gets bigger and bigger, and finally that bag stretches enough where it pops. So what you're doing there is when you squeeze the bag, you're making the volume go down, which pressure goes up. And eventually the pressure builds up so much because you're reducing the volume so much that the bag pops. This is an inverse relationship, meaning if one goes up, the other goes down. So they do opposites. And again, you should be able to recognize its graph. This is called Boyle's law. And we'll do a lab near the end of the school year regarding Boyle's law. Another thing I want to talk about is changing the number of particles, basically adding more gas. If we think about if our car tires or bike tires are running low, what do? We pump more gas into them. So temperature and pressure are relatively constant, and by adding more gas, you'll increase the volume of the tire. So the tire gets bigger and it doesn't run flat anymore. If temperature and volume are constant, adding more gas will cause an increase in pressure. So that makes sense. If we have a can, some sort of metal can, its volume doesn't change. We keep it at a constant temperature. If we add more and more gas, the pressure will increase. If pressure and volume are constant, adding more gas will require a decrease in temperature. So in order to keep the pressure and volume constant, if we keep adding more gas, we would need to decrease the pressure so that the particles are moving slower to keep the pressure constant. And then the opposite is true if we remove gas. So those are just kind of the explanations of the relationships. These are the actual gas laws. So these are the equations. Why didn't it highlight all of those? That's weird. Huh. Well, these are your gas laws. These will be given to you. You do not need to memorize these. You will want to remember the ideal gas law, PV equals nRT, and I'll do a separate video on that in a day or two here. And Dalton's law of partial pressures. We're going to talk about these first, though. These are the laws that you will use, the formulas you will use for the gas laws practice quiz. So either copy these equations down here. I still don't know why it doesn't highlight those. That's weird. So copy down these formulas or print out this page of the notes or all the notes, preferably, so that you have these equations for when you do the gas laws practice quiz. You will want those. Yeah, and we'll do some examples here in a second on those. The last thing I want to talk about, I'm going to come back to the ideal gas law. The last thing I want to talk about in this video is the Dalton's law of partial pressures. And basically what it means is if we have a mixture of gases, if we have like a scuba tank is for like scuba diving underwater, swimming underwater, a mixture of gases. And the total pressure in that scuba tank is created by each individual gas creating its own pressure. So each gas fills the container independently of the other gases. And each gas exerts its own pressure, which we call partial pressures. So partial pressure could be the pressure from just the oxygen in the scuba tank, or just the nitrogen, or whatever other gases are in there. And basically, Dalton's law of partial pressure says if we take all those partial pressures and add them up, they'll equal the total pressure in the tank. So if we had 3 pressures, we'd use that equation. If we had 2 pressures, we'd just stop after P1 and P2. If we had 4 gases in that mixture, we'd have P total equals P1, P2, P3, P4. It goes on until however many gases you have in that mixture. I just want to do a couple example gas law questions. This is a worksheet that the other modern chemistry classes get. You may also want to have the pressure conversions from the other video, and you'll want to know the temperature conversion. And from the other set of notes, you should have standard temperature and pressure, and also volume conversion there. So to do the gas law worksheet, basically you will want all that stuff there. Some of it's in the notes, some of it's not. So take a minute and copy that down if you haven't already. So to solve these questions, first thing I need Celsius in temperature in Kelvin. For the gas laws to work, temperature needs to be in Kelvin. Problem is we don't really have Kelvin thermometers, so we use Celsius to measure things and then convert it to Kelvin. And we do that by just simply adding 273 to whatever Celsius is. So that's the first thing I'm going to do is I'm going to change any Celsiuses into Kelvin. I'm going to decide which formula to use. We'll talk about that in a second. Write the formula, rearrange the formula for the missing variable, plug in the numbers and solve, do sig figs and units. So here's an example. Actually, let's do this. There we go. So, we have a sample of gas, and it has a pressure of 1.75. So I have a pressure, one of my pressures is 1.75 atmospheres at 55.0 degrees Celsius. So 55 degrees Celsius, that is a temperature. So I have some sort of temperature, and that's 55.0 degrees Celsius. Well, I know that any Celsius temperatures need to be converted into Kelvin, so I add 273, which gives me 328 Kelvin. I gotta have Kelvin, I gotta have temperature in Kelvin. And then I keep reading. It says, what is the temperature? So I'm looking for another temperature. If the pressure is raised to 3.60 atmospheres. So I have another pressure, and that is 3.60 atmospheres. So I look at what I have here. I got two pressures, I got two temperatures. When I look up at my equations, well, there we go. Gay-Lussac's law. T1 P2 equals T2 P1. T1 P2 equals T2 P1. That's the only equation up here that has just temperature and pressure. So that's the one we want to use. And now I've got to figure out which ones are my ones and my twos. And there should be a clue to figure out which one is which. And the clue is right here, is raised to. So it says the pressure is raised to 3.60 atmospheres. So if it's raised to that, that implies that that's the ending pressure. So the 3.60 is my P2, it's my ending pressure. Well, if that's P2, the other P must be 1. And if I notice here, I've got this pressure at that temperature, so they're related. So if 1.75 is P1, the 55 degrees Celsius must be T1. And we're looking for a temperature after I raise the pressure, so that implies that this is T2. So I need to rearrange this equation to get T2 alone. So I'm going to divide by P1. And I get T2 equals T1 P1, oops, P2, sorry. That reminds me to remind you, be careful with the ones and twos. If you get the ones and twos wrong, you will get the wrong answer over P1. So that's the setup. I know all those numbers. I can take those numbers and put them in. I'm kind of running low on time, so what I'm going to do is I'm going to pause the video. So if you want to pause the video at this point, do the math, get your answer, and then check your answer in 1 second. I'm going to pause the video and do the rest of the work, and you'll see the answer in just a second. Okay, there's your answer. 675 Kelvin should have been the answer you got. Again, I'm running low on time, so what I'm going to do is I'm going to do example 2. I'm going to pause it. I'm going to do example 2. So why don't you do the same? Pause the video, do example 2, and then check your answer. And I will have the work up here in 1 second. So those are how the variables get assigned. So P1, V1, V2, and P2. So double check those, make sure you have those right. I'm going to pause it again, continue my work. And there you go. P1, V1 equals P2, V2 is the equation, Boyle's law. I'm looking for P2 because I'm looking for the pressure after I've increased the volume. Increase the volume to 9.25, so that volume is V2. Rearrange it, plug in the numbers, do the math, do sig figs and units. That should be what you got, 4.85. If you have any questions on that, stop by. There is a practice quiz, Gas Laws practice quiz. It has a whole bunch of questions like this. It also has some Dalton's Law questions in there. So if you get stuck on those, stop by and ask.